Hello everyone, my name is Bhanu Durvasula and I'm with Hughes Network Systems. 5G is upon us and evolving at a fast pace. Today I'll be discussing the key drivers for successful integration of satellites into the 5G future. Before I do that, let us first look at the role of satellites in 5G. The 5G network will very much be a network of networks. Satellites have a role to play in four major areas. First, satellites are in a unique position to bring internet connectivity to a large percentage of the world population that is yet to be connected. This will be for providing broadband access to remote locations that cannot be served with terrestrial technology. Second, in urban and suburban areas, satellites can offload traffic from terrestrial network during busy hours and alleviate congestion in these networks. During these hours, delay-sensitive traffic such as voice and real-time applications, they would continue to be served by the terrestrial network, while delay-tolerant traffic like web browsing would be using the satellite backhaul. Another major use of satellites is providing network resiliency. By backing up traffic from terrestrial networks during disasters, when the terrestrial connections are disrupted. Third, satellites can fill in voids in connectivity as users move in and out of terrestrial coverage areas. This will bring in high-speed connections into vehicles, airplanes, and ships with traffic handovers between terrestrial and satellite links and vice versa. Finally, 5G brings in connectivity to billions and possibly trillions of IoT devices. Satellite, with its wide geographic reach, will clearly play a big part in this rapidly growing application. So, no question that satellites will be an integral part of the 5G umbrella of networks. With that, now let me summarize the ingredients for successful integration of satellites into 5G future. I will then go into more details on each of these key drivers. Traditional satellites cannot deliver the high-speed data to keep up with 5G. They're also not cost efficient. There have been significant advances in satellite technology that will enable 5G-like services and complement 5G terrestrial networks. It is not enough to have next-generation satellite technology. You will need ground systems that work well with the satellites, with intelligence and flexibility for efficient use of satellite bandwidth, and to meet required quality of service and at the right cost. Edge computing and content caching will help bridge the gap in quality of experience for users connected with satellite backhaul as compared to users with terrestrial backhaul connections. From an operations perspective, it is very critical for the satellite network segments to blend in with the terrestrial segments and not create a major overhead in provisioning and monitoring for the network operators. Finally, it is essential to have continued efforts in the standards bodies to facilitate convergence of satellite and terrestrial technologies for 5G and beyond. Let us now look at how satellite technology is evolving. Traditional satellites are geosatellites that cover large areas with few beams. These satellites have limited power and so they have less effective throughput. We are now seeing deployment of many HTS or high throughput satellites. For a given geographic region covered by a single large beam by a traditional satellite, the high throughput satellites operate with multiple small beams called spot beams and with frequency reuse. With this, they can provide throughputs in the order of hundreds of gigabits per second. Also, in addition to operating in C, Ku, and Ka bands, they'll be moving up into higher frequency bands like Q and V bands. This will allow satellites to provide terabit capacities. In addition to operation in GEO, we're also seeing more deployments in MEO and LEO. Low Earth orbit constellations have an array of small satellites and many ground stations. These satellites can communicate with each other with the ground stations to provide global coverage for internet connectivity. Of course, the big advantage in using LEO satellites is for significant reduction in latency. End-to-end delays can be anywhere between 6 to 30 milliseconds based on the orbital location of the LEO satellites. These delays are much less than the 280 millisecond end-to-end delay we see with GEO satellites. LEO systems do have more complex processing to handle large constellation and for terminals to perform high rate of connection handovers between satellites. I believe GEO, MEO, and LEO will all have their roles to play going forward. Another major advancement in satellite technology is the onboard processing. Onboard processing allows for regenerative payload where received data streams at the satellite can be decoded and recoded to match channel conditions for the target downlink beam. Capacity reassignment can be done in real time and at a packet level based on the traffic loading. This capability allows packet replication and multicasting. Onboard processing in LEO constellations allows inter-satellite links or ISLs that can be used for communication between regenerative payloads. This will in a big way reduce the need for many gateways and widens the geographic range between a gateway and a terminal. 3GPP standards for satellite integration into 5G have use cases where the satellite can actually take on part or even full G-Node-B functions for supporting the new radio protocols. This will be possible with the regenerative payload capability in the satellite. Another feature is beam hopping. This allows the satellite to dynamically move capacity to beams as and when they need it based on traffic demand or time of the day. Beam hopping makes capacity allocations significantly more efficient than having fixed allocations to beams. In summary, satellite technology with all these advances is moving the right direction for integration in 5G. Bottom line is this evolution will bring more capacity at significantly lower cost. Satellite technology evolution alone is not enough. You will also need next generation ground network that would fit well into the 5G ecosystem. On the gateway side, the trend is towards virtualization of gateway functions. Basically, gateway sites would have RF equipment and modems with all the application layers pushed out into the cloud. Network functions virtualization or NFV cuts down on the need for hardware, simplifies operations by automating network configuration and management tasks, allows greater scalability and significantly improves deployment time for new applications or for network expansion. Typical satellite network has multiple gateways deployed at different geographic locations. Software-defined networking or SDN greatly simplifies routing of gateway traffic to and from the internet during gateway failures or during rain fade conditions at certain locations. A centralized SDN controller figures out best route for given application traffic flow, by looking into things like congestion levels, health of links, and required quality of service. SDN controller also has a visibility over end-to-end traffic flows and pushes security policy updates when there are some as security threats emerge. So NFV and SDN together will bring down both operational and capital costs in a big way. On the terminal side, the technology is moving towards terminals that can support wider channels, higher modulation encoding rates, all leading to higher data rates. For LEO networks, terminal antenna technology must shift, from use of large and expensive mechanically scanning antennas to small and lower cost electronically scanning flat antenna such as phased array antennas. So this is really important. As always, battery life and power consumption in terminals is very critical. This is especially true for IoT devices and terminals that depend on solar power. Another key capability for IoT application is to have satellite terminals that can also aggregate IoT traffic. Finally, for large-scale use of satellite terminals for the various applications, it is essential that the costs of satellite terminals come down significantly. A key success factor for integration of satellite networks into 5G will be to bridge the gap in quality of experience between users that are connected via satellite backhaul and users connected via terrestrial networks. In addition, it'll also be important to not only bridge the QoE, but the gap in access to different types of services available for the two types of users. These include services such as healthcare, education, entertainment, and many others. This can be done by pushing intensive computing and content to satellite terminal location or the edge. Mobile edge computing, or MEC, along with content caching, will reduce latency and increase content delivery speed to provide good user experience. MEC at satellite terminal location will also help distribute compute load across the network and take away this burden from cloud data centers. MEC can also support some IoT applications for performing real-time computations locally at the edge. So combination of MEC with content caching will be very beneficial in satellite bandwidth savings as well as cost savings. It is important to not only look at what would be the drivers for satellite networks with their own segments for 5G readiness, but also equally important to look at drivers on how well they integrate and interoperate with terrestrial networks. To this end, automated orchestration for services and applications across terrestrial and satellite networks will be important. With 5G acting as an umbrella of networks, service provisioning and management should be independent of whether a service traverses a terrestrial link, satellite link, or switches between the two. Use of technologies like SD-WAN to intelligently route traffic between different types of backhaul links will also be key to overall 5G network integration. The backhaul could be different types of satellite links, GEO, MEO, or LEO, in addition to terrestrial links. Network slicing or partitioning network resources among multiple services with different requirements but running on top of same shared infrastructure will also help in integration of satellite into terrestrial networks. Finally, where possible, spectral efficiency can be achieved by dynamically sharing frequency between satellites and terrestrial networks. This can be done on time of the day basis or on a demand basis. Last but not least, continued work from standards bodies like 3GPP will be needed to build on convergence between satellite and terrestrial networks for 5G and beyond. A lot has already been done in defining use cases for satellite. These include service scalability to take advantage of satellites' inherent advantage for multicasting to large geographic areas, especially for video applications. Service ubiquity for providing broadband and cellular services to underserved areas, as well as for public safety and IoT applications. And service continuity for mobility between terrestrial and satellite covered locations. Solutions for a new radio to support non-terrestrial networks are also defined and will be included in the 3GPP Release 17. In summary, satellite is an excellent complementary fit for terrestrial networks under the 5G umbrella. There are a lot of key drivers to integrate satellite into 5G future, and the satellite industry is well on its way to making this a reality. Thank you.